Hello guys, in this video I will explain you how to design a two-way slab using movement coefficient method. We will discuss a simple example like this example question. We are going to design two-way slab using movement coefficient method. Note that this method was published in 1963 ACI. So I will be teaching the American method of this design method. Note that this method is outdated and not published in the current version of the ACI codes. Why? Because currently ACI is following two methods, which are direct design method and another is equivalent frame method. I will teach these two methods in separate video, but this method, movement coefficient method, is still applicable these days and it is widely used in many countries but not in USA. Like India use this method, Turkey also uses this method, okay, but all these countries have modified this method a little bit, but the concept is same. So let us start how to solve this problem. Coefficient method is easiest, quickest and simplest method for two-way slab design. So let us discuss how to solve this. So let me give you a brief idea how to solve. We consider a portion of slab, suppose this square or rectangle, and we will divide that slab into middle strip and edge strip like this. Let this is LB, the greater length of the slab, and the shorter side is LA. Then we divide the slab in such a way that this portion is 1/4 of the edge. Similarly this LA over 4 and this middle portion is LA over 2. Same here, this portion and this portion is 1/4 of the side and this is half of the side. Our main focus is to design for the central strip, that is middle strip, which is this. This strip is along the longer side and this strip is along the shorter side. So we need to design these. Okay, let's understand how the load is distributed in two-way slab. If this is the longer side and this is the shorter side, then we will draw an imaginary line from the corners at 45 degrees inclination. Let me show you. Same from these corners. And then we need to join these. Now these four portions, this represents the distribution of load along the edges. That means this much portion of loading will be transferred to this edge. Similarly, this loading will be transferred to this edge. Same for this side. Now, how do we find the maximum moments created due to these loadings? There are some formulas for it using coefficients. That's why it is called coefficient method. These four equations of moment, these four equations we use. CA and CB are the moment coefficients which are provided in tables. I will show you later. W is the load given, dead load we can calculate, okay, and live load is given generally, or we can assume according to suitable scenarios. Note that one important point, LA and LB are the clear span lengths, okay. That means these are not center to center lengths, these are clear span lengths. See, negative movements generally occurs at the edges of the beam, and positive movement depends upon the continuity condition of the slab. This is the variation of the moment across the slab, but this is shown for the middle strips. For edge strips, these are the edge strips, if you want to design separately, then you can design them for 1/4 of the maximum moment. Otherwise, if you provide same reinforcement details in accordance with the central strip, then it will be fine also, because you are on the higher side. That means you are providing more safety. These are the various slab conditions. These are the various support conditions. What does it mean? See, the first case shows slab is continuous in all directions. This arrow indicates continuity of slab in this direction. So that means this type 1 slab is continuous in all directions. This is discontinuous from this edge. Type 3 long edge is discontinuous. This one is short edge discontinuous, this one is long edge discontinuous. Now 2 adjacent edges discontinuous. Similarly, 2 opposite short edges discontinuous, 2 opposite long edges, 3 edges discontinuous, and all 4 edges discontinuous. Based on the type of support conditions, we have tables for finding the CA and CB coefficient values. You can see from this, what does this ratio? M is LA over LB. Okay, let's go back to our example. Rest of the things I will explain you simultaneously while solving this example. This is the given data. Characteristic strength of concrete is 3000 psi and of steel is 60,000 psi. Live load is given as 100 pound per square feet, and these are the thicknesses of plaster thickness, floor finish. Okay, these two will contribute in dead load contribution along with the slab weight. So let's proceed. What should be our first step? Okay, so this is our first step, calculation of minimum thickness of slab. How do we determine this? Using these conditions given in the ACI 318. And what is alpha F? It is the ratio of the flexural stiffness of beam to slab. In this case, we are going to assume it as greater than 2.0, so that we can use the equation 9.13. Assuming alpha FM greater than 2, we can use this equation for finding the minimum thickness of slab. Now what is Ln here? It is the clear span length which is equals to 30 feet here, and this beta is the clear span length ratio, LB over LA. LB is our 30, that which is the greater length, and LA is the shorter edge, which is 24 feet. So by substituting all these values, we get 0.698 approx feet. Convert this into inches by multiplying this by 12. Comes out to be 8.381 inches. Okay, so this should be the minimum thickness of the slab. So adopt 8.5 inch for better calculation purpose and creating the beam at the time of creation of slab using cement and concrete. Next step is to find the calculation of loads. So WDL, which is dead load. So we have determined the thickness of slab, and we are also given some floor finish thickness and plaster thickness. By adding all the thicknesses, 8.5 is our adopted thickness of slab plus 0.5 plaster's thickness, which is given in the question, and floor finish thickness 1.5 inch, which is already given, times unit weight of concrete. Unit weight of concrete is, we are assuming, 12.5, and we need factored dead load, so times 1.2, because 1.2 is the factor for dead load combination, because you remember WU is 1.2 times dead load plus 1.6 times live load. This whole is WDL. Okay, so upon solving this, we get 157.5 PSF. PSF can also be written as pound per square feet. Similarly, live load. Live load is already given as 100, so factored live load will be 1.6 times 100, which will be 160 pound per square feet. Total load will be WU equals to WDL plus WL directly, because we have already taken the factored loads. So 160 plus 157.5 comes out to be 317.5 pound per square feet. And also, see, we will provide reinforcement somewhere here in our slab. So effective width will be this much. That means we need to subtract this distance, which is called cover or steel. Effective depth D is given by D equals to thickness minus some cover. Assuming cover is 1 inch, we can write this equation: 8.5 minus 1 equals to 7.5 inch. So this will be our effective depth. Now next step is to determine the coefficient values using the tables. We are designing slabs for these 9 portions. Okay, so firstly we need to identify what type of slabs are these. First of all, consider corner slabs. Due to symmetry, we can see that all these slabs have 2 adjacent continuous edges. Okay, and 2 discontinuous edges. So let us identify what kind of slab is this. So 2 adjacent edges, continuous, and 2 discontinuous. So type 4 are the case for corner slabs. So So corners are type 4 slabs. Let us write type 4 here. Okay. Now note that this middle is continuous in all directions. So the middle slab is type 1 because it is continuous in all directions. Type 1. Next, consider these two slabs first. Note that these 4 remaining slabs are not symmetrical. Why? Because these two slabs are having longer edge discontinuous. Longer edge discontinuous. And these two slabs are having shorter edge discontinuous. So let us identify their types. So type 2 and type 3 are the cases in which 3 edges are continuous and 1 edge is discontinuous. Type 2 is for short edge discontinuous and type 3 is for long edge discontinuous. So type 2 and type 3. Now what values of coefficient we need to find? Let us check the moment equations. As I showed previously, these 4 equations we need to use. So we need to find CA, CB, CA positive for dead load, CA for dead load, CB for dead load and CB for live load. These are negative and these are positive. There are different tables for all these different coefficients. Let us find out one by one. See, this table depends upon the value of m, ratio of smaller edge to larger edge, which is 24/30, which is equals to 0.8. So corresponding to 0.8, this one, these are the values. This is CA value, this is CB value. CA, CB, all are negative. Okay, negative. And we have different cases, case 1, 2, 3, 4, 5, 6, 7, 8, 9. Let us check what cases we are having. 1, 2, 3 and 4. So these values we will use. Let us write down these values. .075. Similarly for CB, now let us find CA positive for DL. See, this table represents positive coefficient values for dead loads only. So that means we can obtain CA positive dead load and CB positive dead load from this table. Again, ratio is 0.8. So corresponding to 0.8, we need to use these values. This is CA DL, this is CB DL. So let us write it down. Similarly, let us find the coefficient values for live load using this table. This is for live load. So again, 0.8, we need to use case 1 to case 4 values. Let us write it down. Now one important fact is we need to consider those coefficient values which are the highest among the all types of support conditions of slab. So CA negative will be this value because this is the highest value, so this will be controlling value. Similarly 0.041 here and 0.039 here, 4816 and this. So that means these are the coefficient values we need to use in the moment equations formulas. Okay, now we need to find the values of the moments using the coefficients obtained. As we have obtained all the coefficient values, W also we have already calculated. LA and LB are also known. LA is shorter side 24 feet and LB is 30 feet. Okay, by plugging all these values we can obtain these moment values. Let me write it. Let me write the final values. MA minus comes out to be 13.6 kilo pound feet per feet. I will explain you what does per feet means here. 11.71, 7.96 and 5.15. All units are in kilo pound feet per feet. What does this mean? Let me explain. If this is our slab and right now we are designing it for say central strip, okay, this one along this direction. Similarly we are designing it for this strip in this direction. So I already told you this is half of the side of the strip. So if this is 30, this will be 15 foot. We have obtained the moment in k feet per feet. So according to this moment value you will be getting some steel values, and then according to area of steel you will provide some reinforcement with particular spacing. So whatever will be the reinforcement pattern for 1 foot, and you have designed it for 1 foot only, so same goes applicable for 15 foot throughout the center strip. If you want to provide this in this corner, then it will be safer, but more than safer. Okay, before calculating the area of steel, let us find the depth of the neutral axis. If this is your slab, at a particular depth, say this is A, will be the location of neutral axis. So, and this A value is given by AS FY 0.85 F dash C B. Note that B is 1 foot here because we are designing it for 1 foot. So this is 12 inch. Area of steel we don't know. What is it? FY is 60,000. 0.85 3,000 and this is 12. This comes out to be 1.96 area of steel. Now let us find out the area of steel function in terms of M. Area of steel is given by M divided by M value is changing because we have 4 different values of M. Phi is 0.9 for the given steel and concrete grade. Let us write 60 KSI times D. D is 7.5 minus A. Area of steel is, the depth of neutral axis is 1.96 AS over 2. Note that this moment is in K feet per feet. Okay, so let us change this feet into inch because here we have inch, we have used inch here also. So this will be equivalent to 12 M K inch per feet because we will get the reinforcement area of steel per feet. So using this equation we can find the area of steel for different values of M. So using 4 values of M we can obtain 4 different values of area of steel. Let me write it directly. You can solve on your own to verify these values. Area of steel, this will be in inch square per feet. Now let us find what is the minimum area of steel required, and let us check is there any value which is lesser than the minimum area of steel or not. So area of steel minimum in slabs is 0.18% of gross area. So that means 0.0018 times B into H. So B is 1 foot. 1 foot is 12 inch because we are designing it for per foot, and thickness is 8.5 inch. This comes out to be 0.1836 inch square per foot. So we need to take either this value or any higher value obtained than this value. So this will be controlling value for MA negative. This will be also controlling value because this is greater than AS min. This is also AS. This is also greater than AS minimum. But this is lesser. So for this we will use 0.1836. Okay, next step is to find the spacing and the bar selection according to the area of steel. For uniformity, let us choose 510 mm bars. So area of one bar will be AS equals to pi by 4 times 10 mm square, which will be 78.54 mm square. Now let us convert this into inch square. This will be approximately 0.121 inch square. So now how do we calculate the spacing? Spacing will be given by area of one bar times width divided by required area of steel, which we have already calculated for different moment values. So let us find out the spacing for positive moment along the shorter direction. So that will be equals to area of steel of one bar, which is equals to 0.121 times width is 12 inch divided by area of steel corresponding to positive moment along the shorter edge, that is 0.244. we have already obtained. This comes out to be 5.95 inch. So let us adopt spacing 5.5 inch center to center. Okay, more closer spacing is more safer. Now let us find the spacing in shorter direction but for negative moment. See, in this case we have already provided some steel, so we need to subtract area of steel already provided from the area of steel required in the negative section. So area of steel already provided is given by area of one bar times width divided by 2 times spacing, which we have already provided in that direction. So 0.121 12 inch divided by twice of spacing. Spacing you have already provided in this direction is 5.5 inches. So 5.5 times 2 is 11. This comes out to be 0.132 inch square per feet. This much area of steel has been already provided. So remaining area of steel to be provided equals to required one is 0.427. Subtract this 0.132. This comes out to be 0.295 inch square per feet. So spacing will be 0.121 times this much and this much area of steel, the remaining area of steel, this comes out to be 4.92 inches. So let us provide 4.5 inch spacing center to center. This is along the shorter direction. Similarly, along the longer direction, but for positive, that will be equals to area of steel of 1 bar times 12 divided by area of steel, which is 0.1836. This comes out to be 7.9 inches. So let us provide 7.5 inch center to center. Now along the longer direction but for negative section, see again we need to calculate the remaining area of steel to be provided, because some area of steel has been provided due to this reinforcement. So let us calculate that. Area already provided equals to area of 1 bar times 12 divided by 2 times of spacing, 2 times of 7.5, this comes out to be 0.0968 inch square per feet. So remaining area or extra area of steel to be provided, 0.365 minus 0.0968, this comes out to be 0.2682 inch square per feet. So this much we need to provide. So spacing will be 0.121 times 12 over 0.2682. This comes out to be 5.41 inches. So provide 5 inches simply center to center. Now let us draw the details of reinforcement. You can see the details of reinforcement from this picture. And I have also provided some torsional reinforcement at the corners according to this criteria. You can see for 1/5 of the span.